Okay. All right. So let me just quickly recall what the divergence of a vector field was on a Riemannian manifold. So if M is a Riemannian manifold, and let's say dvol is a local volume form on a ball in M. So remember, local volume form just depends on a choice of orientation on the ball, right? So there are two possible local volume forms, which just differ by multiplication by plus minus 1. And if X is a vector field on M, then the divergence of X is defined by the equality, the Lie derivative Lx of dvol is equal to the function divergence of X into dvol, right? So this means in particular that the divergence of X is identically 0 if and only if the Lie derivative is 0. And that means if and only if the flow of X preserves the volume form. So if phi t is the flow of X, then the pullback of the volume form phi t star dvol is equal to dvol for all t, where phi t is the flow of X, right? So the divergence is 0 if and only if the flow is volume preserving, okay? And using Cartan's formula that Lx is equal to dIx plus Ixd, we get that since the volume form is an n form, d of the volume form is 0 because it's an n plus 1 form. So this becomes simply d of Ix dvol, right? And we proved last time the divergence theorem that if you take a domain with smooth boundary, a compact domain with smooth boundary in the manifold, then at any point of the boundary, you can define a unique outward unit normal. If your manifold is oriented, then using the orientation, you can choose at each point an outward unit normal, right? It's defined by the fact that at any point there are two choices of a unit normal, either outward or inward. So how do you say which is outward? Well, in a chart on the boundary, right, the derivative, if the chart maps the boundary to Rn minus 1, the boundary of the upper half space, then the derivative of the chart will map the outward unit normal to a vector which points out of the upper half space, right? So that's how you define an outward unit normal. Yeah. And the orientation on the boundary is defined using the outward unit normal. Okay. So the divergence theorem says that the integral of the divergence of a vector field X with respect to the volume form over the compact domain D is equal to the integral over the boundary of D of the inner product of X with the outward unit normal ds. Okay, where ds is the volume form of the boundary of D. Okay, so this was the divergence theorem which we proved last time. So are there any questions? Any questions?
No, sir.
Okay. Yes. Question? Yeah. Yeah, question?
Sir, no.
No, sir.
No questions? Okay. So we also proved if phi is a smooth function, then we its root x is plus the of grad phi with x, right? Okay. So this last formula, f is a C2 function on n. Okay. Then the Laplace of f. So you take the gradient vector field. Okay. So that's C2. This will be a C1 vector field. And therefore you can define its divergence. Okay. So you take the divergence of the gradient vector field of f. All right. So this is a continuous function. Okay. Or in general, if you take f to be ck plus 2, k is non-negative, then the Laplacian will be a ck function. Okay. Is this clear? Yeah. Yes. All right. Okay. So okay. So this Laplacian, you can see it's going to be a second order differential operator. Okay. Because first of all, remember, if we derive an expression for the gradient vector field, so if the matrix G upper ij was the inverse of the matrix G lower ij, G lower ij was the matrix of the Riemannian metric, right? Then grad f was sum over I of sum over j, G upper ij, del f del xj, the whole thing, del del xi, right, in local coordinates. Yes? Okay. And we can derive an expression for the divergence. So where is it? Let me see. Yeah. So we can derive an expression for the divergence in local coordinates, which will show us that it is a first order differential operator acting on the coefficients of our vector field x. Okay, so suppose x is a smooth vector field, and I take a chart u comma phi, where phi has components x1 to xn. So then x I can write as summation some x upper I del del xi, right? Where x upper I are the components of x with respect to the basis del del xi. So then my local volume form dvol I can write as the square root of the determinant of G into dx1 wedge dxn, right? This we already saw. So we know that the divergence is defined using the Lie derivative of the volume form, which is given by Cartan's formula by d of ix dvol. So we need to compute this d of ix dvol, right? So let's first compute ix dvol, the interior contraction ix dvol. So Ix dvol will be what? Dvol is square root determinant G into dx1 wedge dxn. So Ix dvol will be square root determinant G into Ix of dx1 wedge dxn. Now, this is an n-1 form, right? So with respect to the basis of the n-1 forms, those will be given by linear combinations of wedge products, dx1 wedge dxn with dxj omitted, right? And the coefficient of this is a basis element of the space of n-1 forms. So the coefficient of this basis element will be the form that we're looking at applied to the basis vectors del del x1 up to del del xn with del del xj omitted, right? So Ix of this form acting on these n-1 vectors, del del x1 up to del del xn, means that you have to insert an x in the first coordinate, in the first position, and then act on the remaining n-1 vectors. So this will be dx1 wedge dxn acting on x comma del del x1 up to del del xj minus 1, then del del xj plus 1 up to del del xn. This into dx1 wedge dxj minus 1 wedge dxj plus 1 wedge dxn. Is this okay? Yeah. All right. Now what can I do? Now x is equal to sum over I xi del del xi. So when I write that, if I substitute x here, right, as summation over I xi del del xi, then you see if I is not equal to j, then, so first of all, by multilinearity, this will become a sum over I, right? Xi, and then inside I'll have del del xi, and then del del x1, del del xj minus 1, del del xj plus 1, del del xn. So if I is not equal to j, then del del xi will be repeated twice, right? Del del xi will be repeated twice if I is not equal to j. And so therefore this will become 0 because it's an alternating form. So the only term which remains is when I is equal to j, right? So then I'll have a del del xj here. I'll have xj outside, and I have dx1 wedge dxn acting on this, okay? Now what I can do is, I move this del del xj into the jth spot, right? So to do that, I'll have to make j minus 1 transpositions. So I'll get a sign minus 1 to the j minus 1, xj, and then I'll get dx1 wedge dxn acting on del del x1 up to del del xn. That is equal to 1. So that goes away. And then I'll just have dx1 wedge dxj minus 1, wedge dxj plus 1, wedge dxn. All right. So this is the interior contraction Ix dvol. It is square root determinant G into sum over j minus 1 to the j minus 1 xj dx1 wedge dxj minus 1 wedge dxj plus 1 wedge dxn. Is this okay? Yeah?
Yeah.
Okay. So now we want to compute the divergence. So we know that divx into dvol is d of Ix dvol, right? So I have to take d of this expression here. So this will be sum over j minus 1 to the j minus 1. D of this square root determinant g into xj into this, right? So then I use the definition of the exterior derivative. For each term, this will be a sum over, this will be d of this function, wedge this n-1 form. So d of this function is sum over I del del xi of square root determinant g into xj dxi. And then I have this wedge product. Okay. Now I'll get a sum over ij, but again, if I is not equal to j, then dxi will occur over here and also over here. So dxi will occur twice, but we know that the wedge product is alternating on one forms, right? So dxi wedge dxi is 0, right? And the wedge product is associative. So that dxi wedge dxi, which is 0, will give that these terms are all 0 if I is not equal to j. So the only term which will remain is when I is equal to j. So then I'll get sum over j minus 1 to the j minus 1 del del xj of square root determinant g into xj, then into dxj, and then wedge this dx1 wedge dxj minus 1, wedge dxj plus 1, wedge dxn. Okay. And now what I can do is I can move this dxj back into the jth spot here. But again, to do that, I'll need to make j minus 1 transpositions. So that will again give a sign of minus 1 to the j minus 1. So that into this minus 1 to the j minus 1 will give me just plus 1. Okay. So then finally what I'll get is that I'll get dx1 wedge dxn common. So I take that common, and then inside I'll get a sum. Sum over j del del xj of square root determinant j g into xj. Okay. So I want to get this in terms of the volume form. So to get the volume form, I multiply by square root determinant g and I divide by square root determinant g. So then this last term on the right hand side will become dvol, and I'll get a 1 over square root determinant g here. Okay. So I get this function into dvol, that is equal to div x into dvol. So therefore div x is equal to the function 1 over square root determinant g into sum over j del del xj of square root determinant g into xj. All right. Is this clear? Yes.
Yes.
Yeah. Okay. So that shows you that the divergence is a first order differential operator, right? It's a first order differential operator acting on the coefficients of the vector field. So if I use that here, that if x is equal to sum over I xi del del xi, and then divergence x is equal to 1 over square root determinant g into sum over j del del xj of square root determinant g into xj, right? So what will this give me? So what will the first order terms be? The first order terms will be when I differentiate xj and leave the square root determinant g untouched. So that square root determinant g will cancel with this square root determinant g. So the first order term will be sum over j del del xj of xj, right? So that is the same expression. And then I'll have the derivative of this square root determinant g. So that will be what? That will be 1 over, so 1 over 2 square root determinant g into the derivative of determinant g. So yeah, so let me just write this as sum over j del del xj of square root determinant g divided by determinant g. All right. When you sum over I. Okay, let me make this a sum over I. I'll make this a sum over I. So, okay, so I'll just write out what you get. So what you'll get is the highest order term. It's easy to see. It will be sum over I. G upper. So see, the highest order term will come when I differentiate f and leave the Gij's alone, right? So that will give me Gij into del squared f del xi del xj, right? And then I'll have lower order terms. That means lower derivatives of f. So first and 0th order derivative. Of f. Okay. Is that clear? Yes?
Yes, sir.
Okay. So this is an example of what's called an elliptic second order linear differential operator. You can see it's a second order operator, right? It's got second derivatives. And why it's called elliptic is because this matrix Gij, which is coming here, at least on compact sets, this is strictly positive definite. So it's bigger than or equal to some epsilon times the identity matrix. It's a symmetric matrix, right? It's the inverse of a symmetric matrix. So it's a symmetric matrix. This symmetric matrix is positive definite on compact sets, right? So it's positive definite with the lowest eigenvalue strictly bounded by some positive constant epsilon. Okay. So if you have a linear differential operator of second order operator of this form, some sum over ij, aij, del squared f, del xi, del xj plus lower order terms, then you'll say the operator is elliptic if this coefficient matrix aij for the second derivatives, that is strictly positive definite with a uniform lower bound on the lowest eigenvalue on a given compact domain in your manifold. Okay. Yeah. So if the whole manifold is compact, then it will be elliptic on the whole manifold. Yeah, that's all right.
What is it for non-compact manifold? So you can only
It may
say
not
that
be, no, it may not be
you can
strictly
only,
elliptic. Yeah, it will be positive definite, but this epsilon may go to 0 as you go to infinity in the manifold.
okay.
Yeah, that's it. So on a non-compact manifold, typically what happens is the Gij's, the lowest eigenvalue goes to 0. So this epsilon is the lowest eigenvalue, right, of this positive definite matrix, right?
Yeah.
So that lowest eigenvalue can go to 0 as you go to infinity. Yeah. So on a non-compact manifold, it may not be strictly elliptic. Okay. All right. So this is the Laplacian in local coordinates. And I want to relate this to the Hessian matrix. The Hessian, which was remember, it was a self-adjoint linear map, right? From the tangent space to the tangent space, which played the role of the second derivative of f. So it was a vector v went to the vector nabla sub v of grad f. Okay. This was the Hessian, right? And yeah, so I want to relate the Laplacian to this Hessian. So to do that, we'll need a little bit of work. So it'll be useful to introduce this notion of what's called a parametrized surface in a Riemannian manifold. So that will just be a smooth map from an open set in R2 into the manifold. Okay. So now, just like we had the notion of a vector field along a curve, similarly, we have the notion of a vector field along a parametrized surface F. So this will be a smooth map V from the domain of the parametrized surface in R2 into the tangent bundle Tm, such that the vector V of St belongs to the tangent space at F of St. Okay. And now, given a vector field along a parametrized surface, just like if we had a vector field along a curve, we could look at its covariant derivative along the curve. Similarly, for a vector field along a surface, we can define two vector fields, capital dV del S and capital dV del T. So these are sort of partial covariant derivatives with respect to S and T. So how do you define dV del S at a point S naught T naught? What you do is you fix T equal to T naught and look at this V as a function of just S, right? So then S goes to V of ST naught. This is a vector field along a curve. The curve is S goes to F of S comma T naught, right? So it's a vector field along a curve. So I can take its covariant derivative along that curve. All right, d del S of this vector field along the curve. This is defined to be dV del S, okay? And similarly, you can define dV del T by fixing S equal to S naught and taking the covariant derivative with respect to T, okay? Now, given a parametrized surface, we always have two vector fields along the surface, del F del S and del F del T. Where what is del F del S? Well, you fix T equal to T naught, and then you look at the curve S goes to F of S comma T naught. So this is a curve in the manifold. You take its tangent vector. Okay. So dds at S equal to S naught of this curve. So that is defined to be del F del S. Okay. At S naught T naught. Similarly, you can define del F del T. All right. Okay. Now we want to prove two. Well, I want to state at least two important properties of parametrized surfaces, which will be useful for us. So,
I had a question. What was the difference between the two vector fields you defined? One was covariant derivative, and the other was just.
oh yeah. So
So
one was I'm given a vector field V along F, then I define dV del S and dV del T. All right.
yeah, okay.
The other is I'm defining two vector fields associated to F, del F del S and del F del T.
Okay. Yeah.
Right. So these are the analogs. Like if I had a curve, then associated to the curve gamma, I have the tangent vector field gamma prime T, right?
Yeah.
So these are the analogs of gamma prime T, except because I have two coordinates, S and T, I get two vector fields along F, del F del S and del F del T. That's all.
Yeah. Okay.
Okay. So let me look at a special case. Suppose F is a diffeomorphism onto a two-dimensional submanifold S of n. Okay. So suppose F is an embedding. This may not be true, but suppose F is an embedding. Then my vector fields del F del S and del F del T, these are defined on a submanifold, and that I can extend to a neighborhood of the submanifold, right, locally. So that means that del F del S, I can write locally as X composed with F. and and del f del t I can write as y composed with f, where x and y are two vector fields on a neighborhood of a point in the submanifold. Okay. Yeah. This is because I have a submanifold, right? So, and f is an embedding. So I can do this. Is that clear? Yeah. And then by definition, if I look at the vector fields del del s and del del t, these are the coordinate vector fields on R2, then del del s is f related to x, right? And del del t is f related to y, right? Okay. So I know that, therefore, the bracket of del del s and del del t will be f related to the bracket of x and y, right? But the bracket of del del s and del del t is 0. So that means that x bracket y is f related to 0, right? So that means that the bracket of xy is 0 on a neighborhood of this point f of st naught in the submanifold S, right? So in the submanifold S, these two vector fields commute, all right? X and y are tangent to the submanifold S, and their bracket is 0 in S, okay? Now suppose I look at del f del S, and I take its covariant derivative with respect to t. So I look at capital D del t of del f del S. So what is this? This is the covariant derivative of the vector field along a curve. T goes to del f del S of S naught comma t. This is x of f of S naught t, right? So this is the covariant derivative of a vector field in the manifold restricted to this curve. Therefore, this is going to be nabla sub gamma prime of x, right? Where gamma is this curve. And what is the derivative of this curve? If I differentiate in the t variable, I'll get del f del t, which is given by y. So this will become just nabla sub y of x. Okay. This d del t of del f del s, it will become nabla sub y of x. Similarly, d del s of del f del t, this will become nabla sub x of y. But now we know that the bracket of xy is 0 at this point on the image of f on the submanifold S. So therefore, by symmetry of the connection, right, we know the Levi-Civita connection is symmetric. That means that nabla xy minus nabla yx is bracket xy. So if bracket xy is 0, that means that nabla yx will be equal to nabla xy. And therefore, we'll get that d del t of del f del s will be equal to d del s of del f del t. All right. Is this clear?
Yes.
Okay, so symmetry of the connection will imply this property. If I take a parametrized surface, which is an embedding, d del t of del f del s is equal to d del s of del f del t. Okay. So we have less than a minute. Let me stop this session and start a new one. Okay. Okay. So yeah, okay. So we get that this property holds if f is an embedding, d del t of del f del s is equal to d del s of del f del t. Okay. And now similarly, if we have any vector field v along f, right, then again, because f is an embedding, we can think of the vector field v as a vector field on the submanifold and then extend that locally to a neighborhood in M. So locally we can write v as a vector field z composed with f, okay, where z is a vector field in a neighborhood of the image of the point S naught T naught, a neighborhood in M, okay. And then similarly to what we did above, we see that dv del s will be equal to nabla xz composed with f, right, where x was the vector field which when restricted to the surface gives you del F del S. And similarly, dV del T will be nabla YZ, right? Where again, Y was the vector field, which when restricted to the surface gives you del F del T, okay? So therefore, if I apply this again to this vector field nabla XZ, what will d del T of d del SV be? It will be nabla Y of nabla XZ, and similarly d del S of d del TV will be nabla X of nabla YZ. So what will the difference be? It will be nabla Y nabla XZ minus nabla X nabla YZ. But now nabla sub bracket XY is 0. I mean, the bracket of X and Y is 0 on S. So this becomes what? This becomes the curvature of the Levi-Civita connection applied to Z, right? R of XY applied to Z, composed with F. Okay. So I haven't defined the Riemannian curvature tensor, but that's just a special case of the curvature of a connection on a vector bundle. Okay. So let me just remind you the definition. Yeah, so the curvature of a vector field, of a vector bundle with a connection, was a map from vector fields, cross sections of the vector bundle, gamma E, two sections of the vector bundle, gamma E, right? Yes, you remember the curvature of a connection on a vector bundle? So if the connection is the Levi-Civita connection on the tangent bundle, then we get what is called the Riemannian curvature tensor. Okay. Is this clear? So R of XY applied to a section of the tangent bundle Z, which is just a vector field, will be nabla Y nabla XZ minus nabla X nabla YZ plus nabla bracket XYZ. Okay. Is this clear? Yeah, we defined this for any connection on a vector bundle, right? So in this case, we're taking the connection to be the Levi-Civita connection and the vector bundle to be the tangent bundle. All right.
Yeah, it's clear.
So it's a special case of connection on a curvature of a connection on a vector bundle. Okay. This is called the Riemannian curvature. Okay. All right. So for this parametrized surface, what do we get? We get that this d del T, d del SV minus d del S, d del TV, this becomes equal to R of XYZ composed with F, right? Because bracket XY is 0 on the submanifold S. Is this clear? So the third term in the curvature expression vanishes. Right, this third term, nabla sub XY, this vanishes. Okay. Is it clear? Yes?
Yes, sir. Yeah.
Okay. And what is R of XYZ composed with F? So X and Y correspond to del F del S, del F del T, and Z corresponds to the vector field V. So finally, what we get is that d del T dV del S minus d del S dV del T. So that means the difference of these two covariant derivatives is equal to a curvature term, R of del F del S, del F del T applied to V for any vector field V along F. Is this clear? Yeah.
Yeah.
So actually, these we've proved under the assumption that F was an embedding, but actually these properties hold for any parametrized surface. You do not need to assume that it's an embedding. What we have is that for any parametrized surface F, we have d del S of del F del T is equal to d del T of del F del S, right? So this is something which follows from symmetry of the connection, symmetry of the Levi-Civita connection. And the second property is something which follows from the definition of the curvature tensor, d del T of dV del S minus d del S of dV del T is R of del F del S, del F del T applied to V for all vector fields V along F. All right. Okay. Yes.
Sir, like the last part you had defined x as del f del s and y as del f del t, right?
Correct, correct. Yeah, that's right. Yeah.
Like they had access to vector fields x and y such that exist.
Yeah, such that del f del s I could write as x composed with f, and del f del t I could write as y composed with f. So this was only under the assumption that my surface was an embedding, right? It was a diffeomorphism onto a submanifold of M. But what I'm saying is that, so we use that assumption that it's an embedding to prove these properties. But what I'm saying is actually these properties hold anyway, whether or not the map is an embedding or not. Okay. These two properties hold anyway for any parametrized surface. So you don't need to assume it's an embedding. All right.
I see. Okay.
So the proof of this you can try and prove as an exercise. All right. So what you'll have to do is you take a chart on M. So x1 to xn are local coordinates. So you compose your chart with F, then F becomes a map into Rn, right? F becomes a map into Rn. And then you can write these del F del S and del F del T. You can write in terms of linear combinations of del del xi's with coefficients which are functions of S and T, right? And similarly, any vector field V along F, you can write as summation, some AI of ST into del del xi, right? Is it clear? And then you have to calculate and show that these expressions are equal, okay? So there's
So
some calculation.
Parametrized surface is locally an embedding, right? And this is a
No.
local Okay.
No. It may not be locally an embedding. No. Just think of the one-dimensional case. You have a curve. A curve may not be locally an embedding, right? There are points where it may not locally be. So similarly, a parametrized surface, you just add on an extra coordinate, and in one direction, it won't be an embedding locally. So no. It may not locally be an embedding. No.
Okay.
Yeah. For that, you need DF to be injective, right? But there could be points where DF is 0 and where that's an accumulation point of other points where DF is 0, right? That could easily happen. And it's still a smooth map. So that
Oh, parametrized surface just means it's a smooth map. There's no
Yeah.
condition on the rank also. Okay.
No.
Okay.
This embedding, I assume, just to give you a simple proof of these identities. That in this case, I mean, it's to motivate these identities. It's just to motivate these identities. It's just for motivation purposes. It's not for the purposes of a proof. No. For a proof, what you have to do is decompose vector fields along F into the coordinate vector fields del del xi with coefficients which are functions of S and T. And then you have to compute. Okay, you have to compute. All right.
Yeah. Okay.
So that's the way to do it. You always have to decompose into the sum of linear combination of the basis vector fields del del xi. Yeah. So okay. So I'll leave you to prove these two as exercises. Okay. Why I did this? I want to apply this to get another formula for the divergence. Okay. As follows, in terms of a trace. So trace of some linear map. Okay. All right. So let X be a vector field on M and let phi t be the local flow of X. Let dvol be a local volume form. Okay. So we know that divx into dvol is the Lie derivative Lx dvol. So this is equal to ddt at t equal to 0 of phi t star dvol. Now, phi t is a map from a Riemannian manifold M into itself. So we know that for a map between Riemannian manifolds, when you pull back, the volume form gets multiplied by the determinant of the linear map, right? The determinant of the derivative of the smooth map. So where that determinant is the determinant computed with respect to positively oriented orthonormal bases, right? We saw this last time, right? When I pull back the volume form by F, I'll get determinant dF into dvol, right? Yes?
Yeah, right.
Right, we saw that. So this becomes ddt at t equal to 0 of determinant d phi t into dvol. So this dvol is fixed, so I can take it outside the derivative. So this becomes ddt at t equal to 0 of determinant d phi t and then into dvol. All right. So now look, where is d phi t going? It is going from the tangent space at P to the tangent space at phi t of P. Okay. So what I want is a linear map which goes from the tangent space to itself. So for that, what I can do is I look at the square of the determinant, right? This I can write as the determinant of d phi t star d phi t, right? D phi t star d phi t, this will go from the tangent space back to itself. Yes? Okay, here d phi t star, this is the adjoint of a linear map between inner product spaces. So the adjoint will go in the opposite direction, right? From the tangent space at phi t of P back to the tangent space at P. All right? So when I compose the two, I'll get an endomorphism of the tangent space. Is that clear? Yes?
Yeah, right.
Right, I'll get an endomorphism. Okay. Now when I get an endomorphism, I'm in good shape because then I can use the calculation we did in the beginning of the course. So I have to compute this ddt of determinant phi t, right, at t equal to 0. So first I compute determinant ddt of determinant phi t squared. So this becomes ddt of determinant of d phi t star d phi t, right? But now this is the derivative of the determinant of a family of endomorphisms, right? But I know that for endomorphisms, when I apply the determinant, the derivative of the determinant at the identity, that is the trace, right? We did this calculation earlier.
Yes.
And when t is equal to 0, this endomorphism is the identity, right? Because d phi 0 is just the identity. So at t equal to 0, this gives me the identity. So I'm differentiating determinant of some family of matrices AT, passing through the identity at time t equal to 0. So this is going to be trace of the derivative of this family of matrices, right? So this is going to be trace of ddt at t equal to 0 of d phi t star d phi t.
So,
Okay.
sir, that's basically the derivative of all the singular terms of phi t, right? Of the linear map d phi t. I mean, square of the singular values.
The sum of
Singular
squares,
values, yeah.
sum of squares, yeah, sum of squares. So it's a derivative of the sum of squares, yeah.
Right.
Okay, anyway, let's compute this derivative. Okay, so it's a trace of this derivative and trace is linear. So I can write this as ddt at t equal to 0 of the trace of d phi t star d phi t, right? Because trace is linear, so I can take it inside the derivative. Okay. Yes?
Yeah.
Now, these are endomorphisms of an inner product space TPM, right? So what is the trace? To calculate the trace, I can take any orthonormal basis EI and apply this endomorphism to EI and take inner product with EI and then sum over I. This is the trace, right? Yes? This is the trace. So I'm taking ddt at t equal to 0 of this sum. And now this sum, this d phi t star, I can take onto the right-hand side. So this becomes inner product of d phi t EI, d phi t EI, sum over I. Okay. All right.
Yes.
Now what I can do is this derivative d phi t of EI, I can do the following. What I do is I take up the following parametrized surface. I choose geodesics gamma I such that at time 0, they pass through P and gamma I prime 0 is equal to EI. Okay. Then I define a parametrized surface. Fi of ST is phi t of gamma IS. Okay. All right. So this is a function of two variables taking values in M, right? phi t of gamma is. Now, what happens if I take del fi del s? That means I'm going to differentiate with respect to s at s equal to 0. That will mean by the chain rule, it is just d phi t of ei, right? Yes. So this d phi t of ei, I can write as del fi del s, del fi del s. Okay. At 0, t. All right. Now I have to, now I differentiate this with respect to t. And for this, I can use the the metric compatibility of the Levi-Civita connection. So I can take this ddt inside, right? And I'll get a covariant derivative, capital D del t. And I'll get twice this because I'll get two terms from the Leibniz rule. Both of them are equal. So I'll get twice the sum over I, capital D del t, del fi del s at 0, 0 of ei, inner product with ei. Now we can use the property of parametrized surfaces, which follows from symmetry of the connection. D del t del fi del s is the same as d del s del fi del t, right? Yes?
Yeah.
Now, what is del fi del t? So here fi is phi t of gamma is. So if I differentiate with respect to t, what will I get? Because phi t is the flow of the vector field x, this is going to give me the vector field x at the point gamma I of s, right? So del fi del t will be x of gamma is, right? And then I have to take dds at s equal to 0 of this. But now gamma I is a curve whose tangent vector at time 0 is ei. So dds of x of gamma is, this will be nothing but nabla sub ei of x, right? Yes? Okay. So finally, what do I get? I get 2 times the sum over I, nabla sub eix, inner product ei. Okay. And this was the derivative of determinant d phi t squared by the chain rule, that is equal to 2 times the determinant of d phi 0. That's the determinant of the identity. That's 1 into ddt of determinant d phi t. So what I want is this ddt of d phi t, determinant d phi t. I divide by 2 here, so that will cancel with the 2 here. So finally, what I get? Yes.
In
Yes.
the first line that you have currently on the page, like 2 times over I inner product t del fi del s 0, 0,
Yes.
s 0, 0. So you are taking the partial derivative of fi at 0, 0, right? And then taking the co-derivative, covariant derivative d del t.
No, no. No. I'm taking the partial derivative at with respect to s at time s equal to 0 and at some t. Then I'm differentiating with respect to t, right? At t equal to 0.
Yeah, and then you are and then by the property, so you are interchanging that. So d del s del t, right?
Right.
Of
Del
that
fi del t, yeah. At
so
0.
that del fi del t at 0, 0 means del fi.
No. You're misinterpreting. No. Let me explain. No. No, wait. This is just a matter of partial notation about partial derivatives. This is what I'm writing is, say, d del s del f del t. If I write this at 0, 0, what it means is this whole vector field evaluated at 0, 0. This is a vector field along f. This whole vector field along f evaluated at 0, 0. So what does this mean? In steps, this means d del s at s equal to 0 of del f del t at s comma 0. That's what this means.
Yes. Oh, I got it. Sorry.
Got it? Okay. So now is the computation clear?
Yeah, it's clear.
Okay. So finally, what do we get? If I cancel the 2's, what I'll get is that this ddt at t equal to 0 of determinant d phi t, this is equal to my divergence x, right? This becomes the sum over I, nabla sub EIX, inner product with EI. Now this I can write as the trace of a linear map called nabla x, where what is nabla x? This is a linear map from the tangent space to itself. It's the endomorphism. V goes to nabla sub V of x, right? Is that clear? This is an endomorphism. V goes to nabla sub V of x, right? And what I'm doing is I'm taking this endomorphism applied to EI and then inner product with EI and then sum over I. So that is the trace of this endomorphism, right? Yes?
Yeah.
Okay. So what is this? What I'm getting is finally that the divergence of x is the trace of nabla x. Okay, so this gives me another formula for the divergence. All right. So from this formula, we immediately get that the Laplacian will turn out to be the trace of the Hessian, just like in Euclidean space, because here I have my function f, my vector field x is nabla f, the gradient of f, right? So what is nabla x applied to v? This is nabla sub v of x, that is nabla sub v of grad f. That by definition is Hessian f applied to v. There's a typo here, there should be a v here, right? This is Hessian f applied to v, right? So this linear map, nabla x, is nothing but the linear map Hessian of f, right? Is that clear? By definition of the Hessian, okay? And therefore the Laplacian of f, this is the divergence of grad f, which is the divergence of x. This is the trace of nabla x, which is the trace of the Hessian of f. All right? Okay?
Yeah.
Okay, so therefore the Laplacian of f is the trace of the Hessian of f. Okay? Is this clear? Yeah?
Yeah, it's clear. Yeah.
Okay. So fine, let me just recap. So divergence of x is equal to trace of nabla x, where nabla x goes from TPM to TPM. V goes to nabla Vx. Okay. And if x is equal to Laplacian f, grad f, then nabla x is equal to the Hessian of f from TPM to TPM. Right? V goes to nabla V of grad f. And Laplacian f, which is the divergence of grad f, which is divergence of x, which is trace of nabla x, is just the trace of the Hessian of f. Okay. So we have the same formula as in Euclidean space, right? Is this clear? The Laplacian is the trace of the Hessian. Okay. Is this clear?
Yes, sir. Yeah.
Yeah. So now, in particular, this is something which is useful. If P is a local maximum of F, right? So then we saw that the inner product of Hessian F at P with V, Hessian F times V inner product with V This we could write as a second derivative, d squared dt squared at t equal to 0 of f composed with gamma v of t, where gamma v is a geodesic such that gamma v of 0 equal to p and gamma v prime 0 equal to v in TPM. Okay. So this second derivative, this is less than or equal to 0 because f has a local maximum. So that means the Hessian is less than or equal to 0. This we already saw, right, at a local maximum. And that implies that the Laplacian of f at p, this is equal to the trace of the Hessian of f at p. This is less than or equal to 0. All right. Is this clear?
Yeah, it's clear.
Okay. So at a maximum, the Laplacian is less than or equal to 0. Similarly, at a minimum, the Laplacian is greater than or equal to 0. Okay. So this is useful. So now maybe I should define what is a harmonic function. So, and subharmonic functions. So, superharmonic functions. So, okay. Definition.
This observation you just made, I mean, it sort of gives the definition of subharmonic, right? I mean, so like f is local maximum of it, so it is greater than the average of like the values out around it. So
yes, so let me give you the definition. So f is subharmonic if the Laplacian of f is greater than or equal to 0, okay, and it is harmonic if the Laplacian of f is 0, okay, and it is superharmonic if the Laplacian of f is less than or equal to 0. All right. Is this okay? Yeah.
So subharmonic means the value of f at a point is less than the average of the value of f surrounding
Well,
an average.
that is true in Euclidean space. That yeah. So in Riemannian, so in a Euclidean space, you have the mean value property, right? If f is harmonic, then f is equal to the average with respect to Lebesgue measure of average value over a sphere of radius epsilon around the center, right? If it's subharmonic, then the value at the center is less than or equal to the value, the average value on a sphere around the point. And if it is superharmonic, then the value at the center is greater than or equal to the average value on a sphere. Okay, but in a Riemannian manifold, the situation is a little more complicated. The average, the functions don't satisfy the mean value property a priori in the same sense as in Rn. That is, for a harmonic function, the value at the center is not equal to the average with respect to Lebesgue measure. Instead, you need to take another measure on the geodesic sphere, which is called the harmonic measure. Okay, there is a certain measure called the harmonic measure on the geodesic sphere, which is in general, it is not equal to the Lebesgue measure. And then you have that the value at the center is equal to the value with respect to harmonic measure. Okay.
I see.
So you have to replace the Riemannian measure on the sphere. You have to replace it by harmonic measure. Okay. So harmonic measure is some measure which is absolutely continuous with respect to the Riemannian measure. The Riemannian measure means the surface area measure on the sphere. Okay. With respect to the induced Riemannian metric on the sphere. Okay. So harmonic measure is absolutely continuous with respect to that measure. It's some function times that measure. Okay. But that function is non-constant. Okay. It's not a constant function. There are special Riemannian manifolds where the harmonic measure coincides with the Riemannian measure on the sphere. Those are called harmonic manifolds. Okay, those are called harmonic manifolds. So Euclidean space is an example of a harmonic manifold. On a harmonic manifold, a harmonic function satisfies the mean value property with respect to the Riemannian measure. So other examples of harmonic manifolds are what are called the rank 1 symmetric spaces. So examples of that are, you might know the hyperbolic space or the spheres, Sn, okay? These are examples of rank 1 symmetric spaces. Those are harmonic manifolds, all right? So in general, the mean value property with respect to Riemannian measure is only true on harmonic manifolds, which are a very special class of manifolds. Okay.
I see. Okay. Thank you.
Yeah, in general, you have to take what's called harmonic measure. Okay. In general, you have to take what's called harmonic measure. So since you're asking, I can tell you what harmonic measure is. If any of you are interested in probability, basically you take the point P and then you do, there is a Markov process on the manifold called Brownian motion. So you take Brownian motion starting at the point P, then with probability 1, it's going to hit the boundary of the sphere, the boundary of the ball at some finite time. Okay. And so there is what's called the first exit point from the ball. Okay. So that gives you a random variable on the ball, on the sphere. All right. And then the harmonic measure is the distribution of this random variable. Okay. So let me call it nu sub p, nu sub p r on the sphere of radius SPR. So this is what's called the hitting distribution of Brownian motion started at P. Okay. So yeah, to define Brownian motion on a manifold takes a bit of work. So if you've seen the definition in RM, that's good. If you haven't, well, I can't help you. I mean, that's content for a whole other course. So yeah. Okay. But intuitively, maybe it can give you some idea. Okay. All right. So what happens in the rank 1 symmetric spaces? In the rank 1 symmetric spaces, what happens is, if I look at the isometries of the manifold which fix P, then that acts transitively on the spheres centered at P. Okay, so K sub P, this is the stabilizer in the isometry group. So this acts transitively. on the sphere SPR if M is equal to G mod KP. G is a semi-simple Lie group and KP is a maximal compact subgroup. This is a rank 1 symmetric space. So the action is transitive if and only if the rank of the symmetric space is 1. So if you don't know what a symmetric space is, then yeah, well, I don't want to get into this too much. Yeah. So a symmetric space just means, if I take a point P, you have a map called what's called the geodesic involution, a locally defined diffeomorphism near the point P. Basically, you take a point near P, right? So that is on some geodesic passing through P, right? At a distance, say, T. You map this to the point on the opposite side of the geodesic at distance T. Okay. So this would be I sub P of Q.
Sir, it's less than 1 minute left. So
yeah, okay. So let me just say a Riemannian symmetric space is a map where this local involution, this extends to a global diffeomorphism of the manifold, which is an isometry, okay, which preserves the Riemannian metric. So that is a symmetric space. All right, let me stop this and start. Okay, so let me state, so I was talking about symmetric spaces. Let me just say a little bit. So here, this local, this is called the geodesic involution because it sends geodesics passing through P to themselves, right? This geodesic goes to itself. The point at distance at time T goes to the point at minus T, at time minus T along the geodesic. Okay, so for a symmetric space, this geodesic involution extends to an isometry of the manifold. Okay, that means a diffeomorphism from the manifold to itself, which preserves the Riemannian metric. Okay, so that is a symmetric space. What happens is you can define something called the rank of a symmetric space, which is the maximal dimension K such that there exists an isometric embedding of Rk into the manifold. Okay. A totally geodesic isometric embedding. All right. So yeah, there are many terms I need to define, but I'm not doing that. So yeah. Anyway, let me just say that there's a class of symmetric spaces called rank 1 symmetric spaces, where what happens is if I look at the stabilizer of a point P in the isometric group, this acts transitively on the geodesic sphere. Okay. And then because Brownian motion is natural with respect to isometries, what happens is that means that the hitting distribution of Brownian motion, that will become invariant under the isometric, the stabilizer of P. Okay, so that's some compact group. So that compact group is acting transitively on this sphere. So there is a unique there's a unique probability measure on this sphere, which is invariant under this compact group, which is the Haar measure. Okay. All right. So there's a unique Haar measure, which is on this invariant under this group KP. And the hitting distribution of Brownian motion becomes equal to the harmonic measure, the Haar measure. And so this harmonic measure is nothing but the Haar measure. And also since this isometry group acts transitively on the sphere, that means that the Riemannian measure on the sphere is invariant under the isometry group. Therefore, it is also equal to the Haar measure. Therefore, the harmonic measure equals the Haar measure. Okay. Is it clear? Which equals the Riemannian measure. Okay. So for rank 1 symmetric space, for a rank 1 symmetric space, what happens is that Riemannian measure. So once I normalize this to be a probability measure, okay, on the sphere equals the Haar measure on the sphere, which equals the harmonic measure on the sphere. So these three are equal. In a general manifold, you don't have a Haar measure because you don't have a group acting transitively on the sphere. You still have these two measures, the Riemannian measure and the harmonic measure, but in general, those two are different. Okay. They're equal in the special case of a harmonic manifold. So there are harmonic manifolds which are not rank 1 symmetric spaces. Those are spaces called Dirac-Ricci spaces. Those are certain solvable Lie groups with left invariant Riemannian metric, but I won't get into that. Okay. So, all right. So let me give you some facts. So where should I start? So this is quite a non-trivial fact. One is the solution of the Dirichlet problem. Okay. So we talked about the Dirichlet problem in Rn, right? Given a continuous function on the boundary of a domain. Okay. So suppose D is a pre-compact domain. That means its closure is compact. And suppose it has C3 boundary. Okay. So the boundary is a C3 submanifold. Okay. Then for all continuous functions f on boundary D, there exists a unique U which is smooth in D and continuous up to the closure of D, such that U is harmonic and U restricted to boundary D is equal to F. So this is called the solution to the Dirichlet problem. Okay. So this is a highly non-trivial fact. I won't prove this. This takes quite a lot of work to prove. Okay. Is the statement clear though? Then not exist for all F. Sorry, this is for all F. This is, sorry. Okay.
Yeah, it's
All right. So if you write U equal to U sub F, then we have what's called the weak maximum principle. So it says that if D is a pre-compact domain, so for this I don't need to assume that boundary D is smooth. So if D is a pre-compact domain and U is a C2 function in D, which is continuous up to the closure, such that U is harmonic. So actually there's no distinction between C2 and C infinity here. If U is harmonic, this automatically implies that U is C infinity in D by something called elliptic regularity. Okay. So that means if it's a zero of an elliptic second order operator, then it will automatically be smooth. Okay. So then the SOAP, well, actually, maybe I should state this for subharmonic functions. This is true actually for subharmonic functions. So although then I can't say that U will be smooth, that's all. I can just assume C2. For a subharmonic function which is continuous up to the closure of D, then the SOAP of U over D is equal to the SOAP of U over boundary D. This is the maximum principle, the weak maximum principle. Okay. And so then the harmonic measure is actually a family of measures on boundary D. So suppose D is pre-compact. And boundary D is C3. So we know that a solution of the Dirichlet problem exists. So then for any P in D, define nu P. So this is a linear functional on the Banach space of continuous functions on boundary D, taking values in R. F goes to, so you take the solution to the Dirichlet problem with boundary value F. Let me call that U sub F. This is the harmonic extension of F, and evaluate it at P. Okay, so P is fixed. So this is a positive bounded linear functional. Okay, so the fact that it's bounded linear functional, that follows from the maximum principle, right? This is a harmonic function. So its value at P is less than or equal to the SOAP over the boundary. Similarly, the inf is also greater than or equal to the inf on the boundary. And so the mod is less than or equal to the SOAP of the mod on the boundary. So the mod of this is less than or equal to the SOAP norm of F. Okay. So this is a bounded linear function of norm less than or equal to 1, right? And this is also this is a positive linear functional, because if F is greater than or equal to 0, then by the maximum principle, if I look at UF, the infimum of UF is greater than or equal to the infimum of F, which is greater than or equal to 0. So that means UF of P will be greater than or equal to 0. So this is a positive linear functional, which is of norm less than or equal to 1. And the norm is equal to 1 because if I take F to be the constant function 1, then its harmonic extension is the constant function 1. So this has norm exactly equal to 1. So in fact, this defines a probability measure. Okay, nu P on boundary D. So this is called the harmonic measure. All right. Is it clear? Is the definition clear?
Yes, sir.
Okay, so the fact that this is bounded and positive, that uses the weak maximum principle. All right, that uses the weak maximum principle. Okay. All right, so this defines the harmonic measures. Yeah. And so what happens is you get that the fourth fact is that if say if I take say B is equal to, so so okay, let me just say the fourth fact is the mean value properties. So mean value properties, or maybe say sub mean value property, sub mean value property. So suppose I take U, which is C2 on a ball B and C0 on the closure, okay, where B is a geodesic ball, BPR. Okay. So then if one, U is harmonic on B, then by definition, U of P is equal to the integral over boundary B of U with respect to harmonic measure based at P. Right? This is by definition, really. Do you understand? Yes? This is by definition of the harmonic measure. Is that clear? Yeah, what is the integral of U d nu P? By definition, it is U evaluated at P, right?
Yeah. Yeah.
By definition, this is by definition. This is by definition. Okay. This is by definition. So what is not so clear is if U is subharmonic, on B, then UP is less than or equal to the integral over boundary B of U d nu P. Okay. So this is the submean value property. So the point to note here is that this is with respect to harmonic measure. Okay. This is with respect to harmonic measure, not Riemannian measure. So in Euclidean space, they're equal. The harmonic measure equals the surface area measure. So then you get the usual mean value property. Okay. But in a general Riemannian manifold, you can only use harmonic measure. Okay. Is it clear? Okay.
Yes, sir.
Okay. So 5 is called the strong maximum principle because this implies the weak maximum principle. This says the following, that if so U is harmonic, or let me assume actually subharmonic. So if U is subharmonic, on a connected domain D, then if U attains its maximum at some P naught in D, then U is constant. Okay, so this I can give you a proof of using the sub-mean value property. So you let E be the set of points P and D such that U of P is equal to the maximum value U of P naught. Okay. Then, of course, P naught belongs to E, so it's non-empty. And by continuity of U, E is closed, right? Okay. So what do we have to show? That E is open, then we're done, right? Yes. So claim E is open. And the proof, this follows from the sub-mean value property. So, so let P be a point in E. And let R be positive such that the geodesic ball BPR is contained in D. Okay. Then for all little r less than R, let nu P little r equal to harmonic measure on boundary BPR little r with respect to the point P. Okay. Then what do we know? We know that UP, since U is subharmonic, this is less than or equal to the integral of a boundary BPR, right? Of U d nu PR, right? Yeah, by property 4 above. Because U is subharmonic. Yes, right? But on the other hand, since UP is the maximum, this is less than or equal to the integral of UP d nu PR, right? Over boundary BPR. Yes, so since UP is equal to sup of U over D, right? Is this clear? Yes?
Yeah, it's clear.
Okay.
Yeah.
Right. So that means that the integral of a boundary BPR of UP minus U d nu PR, this is equal to 0. Okay. But and UP minus U, this is greater than or equal to 0 on boundary PPR. Yeah. And now we use a fact. Okay. Well, okay. So this implies that U is identically equal to UP on boundary BPR almost everywhere, right? With respect to nu PR, right? Yes, if I have a non-negative function whose integral is 0, then it is 0 almost everywhere, right? Yes. It's just basic measure theory.
Yeah.
Right?
Yeah.
I have a non-negative function whose integral is 0, therefore it's 0 almost everywhere, right? So this is 0 almost everywhere on the sphere with respect to nu PR, but that implies actually that it's 0 everywhere. Because this is a fact which I won't prove. Because the support of this measure nu PR is actually equal to the full boundary BPR. Okay. And u is a continuous function. So if it's 0 almost everywhere and this measure has full support, then it has to be 0 everywhere. Okay. So, all right. Okay. And this is true for all R in between 0 and capital R. U is equal to UP on this sphere. So this is true for all the spheres. That implies that U is identically equal to UP on the ball BP capital R. Okay. So therefore, E is open, right? So therefore, E is all of D. Is this clear? Okay. So that's the proof of the strong maximum principle. Is this clear?
Yes, sir.
All right. So there's one little fact that we assumed here, that the support is all of boundary BPR. So I won't prove that here. Support means that the full boundary means that no non-empty open set has 0 measure. Any non-empty open set has positive measure. Okay, that's all it means. Any non-empty open set has positive harmonic measure. Okay. That's all. Yeah. Okay. So what do I want to do now? Yeah, so maybe let me finish by talking a bit about curvature. Where was it? Yeah, okay. So let me finish by talking a bit about the curvature tensor and some properties of the curvature tensor we'll need. Okay. So the curvature tensor, as we said, it's the curvature of the Levi-Civita connection on the tangent bundle. So pointwise, I can think of it as an endomorphism valued 2 form, right? From TPM cross TPM to endomorphisms of TPM. VW goes to R of VW. This is a linear map. Z goes to RVWZ. Okay. And as I mentioned earlier, the curvature of a connection on a vector bundle, I can write it in terms of a limit of parallel transport along small quadrilaterals, right? Where I choose 2 vector fields X and Y, whose values at P are equal to V and W, and such that X and Y, their bracket is 0 in a neighborhood of P. Then I take small quadrilaterals where I flow by X for time T, Y by time T, then minus X for time T, and then minus Y for time T. So because the bracket is 0, this quadrilateral closes up. It gives me a closed curve, right? So I call that curve gamma T. And then my parallel transport P sub T, I take to be parallel transport along this quadrilateral. And then my curvature R of VW, one can show this is equal to the limit T tends to 0, PT minus I over T squared. Okay. All right. So then what does that mean? That means that PT I can write as identity plus T squared R of VW plus little o of T squared. Okay. Now, my Levi-Civita connection is compatible with the metric, right? So from that, it's easy to show that the parallel transport acts by isometries, right? Okay. So the parallel transport will act by isometry. So that's easy to see, right? Because if I take any two vector fields along gamma.
That's just compatibility of the connection with the metric, right?
Yes, yes. So you know that, see, DDT of the inner product VW, right? This is equal to inner product dV dt with W, the covariant derivative, plus inner product V dW dt. And this will be 0 if V and W are parallel, right? Because then dV dt becomes 0, dW dt are 0, right? So then this inner product is constant. So that means the inner product between parallel vector fields is constant, right? So that will tell you that the parallel transport acts by isometries. Okay. Is that clear?
Yeah.
Okay. Okay. All right. So we know that parallel transport acts by isometries. So this will imply that the curvature actually will be skew symmetric. That's related to the fact that, you know, the Lie algebra of the orthogonal group is the skew symmetric matrices, right? So an infinitesimal isometry is identity plus a skew symmetric matrix. Anyway, let me just do the computation for you. So we have that PT is equal to identity plus T squared R of VW plus little o of T squared. So let me rewrite this. So let me look at identity. That is, I can write as PT star PT because PT is an isometry. So PT star PT is identity. But this I can write as, using this expansion for PT, as identity plus RV star T squared plus little o of T squared into identity plus RVW T squared plus little o of T squared. So now I expand out this product. It's a matrix product. So when I expand out, the first term will be identity, plus I'll get a term in T squared, which is RV star plus RVW, right? And then I'll get other terms which are little o of T squared, right? So now I just cancel identity from both sides and I divide by T squared and I take this to the other side, and then what I'll get is that RVW star plus RVW is equal to little o of T squared divided by T squared. So this tends to 0 as T tends to 0. So therefore I get that this sum is 0. In other words, RVW star is equal to minus RVW. Okay. So in fact, this endomorphism of the tangent space, RVW, this is a skew symmetric endomorphism. Is that clear? Okay, so the Riemannian curvature, it's an endomorphism valued 2 form, which takes values in skew symmetric endomorphisms. Okay. All right. Is this clear?
Yes, sir.
Okay. So it takes values in skew symmetric endomorphism. The reason for that is the parallel transport takes values in orthogonal transformations. So yeah. Okay. Okay, so we need one little proposition called the Bianchi identity, which says if I take 3 vectors, UVW, then if I look at the curvature tensor applied to these 3, permuted in cyclic order, and I add up RUVW plus RWUV plus RVWU, this gives me 0. Okay. This is called the Bianchi identity. This is just a computation using the definition of the curvature tensor. So you choose 3 vector fields X, Y, Z, whose values at P are equal to U, V, and W, and which commute in a neighborhood of P. We can always do this. Okay. You just take these x, y, z to be linear combinations of the basis vectors del del xi with constant coefficients. Okay, because the coefficients are constant, then the brackets will be 0. Okay? So then what we get is that this RUVW plus RWUV plus RVWU at P, this is equal to RXYZ plus RZXY plus RYZX. Now you write out what this is. Because the brackets are 0, there won't be any bracket terms. You'll get nabla y, nabla xz minus nabla x, nabla yz plus nabla x, nabla zy minus nabla z, nabla xy plus nabla z, nabla yx minus nabla y, nabla zx. Now you group together the terms which have a nabla y. So nabla y will give you nabla y applied to, you'll have a nabla xz here minus a nabla zx, right? But because the bracket of x and z is 0, this nabla xz minus nabla zx, by symmetry, this will be 0. Similarly, you'll get two other terms here, which again by symmetry will be 0. So the whole sum is 0. All right. Okay. So it's just a simple computation. Okay, that's the Bianchi identity. And now the curvature tensor, it's totally determined by this following quadrilinear function. It's a function of 4 vectors x, y, z, t, maps to inner product rx, y, z with t, right? So this will determine the curvature tensor entirely, right? So this this inner product, I'm going to denote it by bracket x, comma y, comma z, comma t. Okay. Then we have the following properties for all x, y, z in TPM. The first property is that this sum, where I permute the first 3 vectors cyclically, this is 0. So this just follows from the Bianchi identity. Then the next property is that if I permute the first 2 vectors, x and y, then this changes sign. So this just follows from the fact that R is alternating in its first 2 arguments. R of xy is minus R of yx. So that gives you the second property. Then the third property is xyzt is equal to minus of xy tz. So if I interchange the last 2 arguments, then it changes sign. That will follow from the fact that R of xy is a skew-symmetric linear map. Let me do the proof of that. So xyzt is inner product rxyz with t. Now I move the operator to the other side as rxy star acting on t, the adjoint acting on t. Now I use the fact that rxy star is minus rxy. So this becomes minus inner product z with rxy t. And this you can see this is just equal to minus of xy tz. Okay. So that gives you the third property. And finally, to finish, we have this last property that if I interchange xy and zt, then this 4 tensor doesn't change. So xyzt is equal to ztxy. So the proof of this is a little computational trick. What you do is you write out the Bianchi identity 4 times, permuting the vectors, and then you add it all up. You'll see that you'll have a lot of cancellations, and what will remain using the earlier properties, you'll have cancellations, and then you'll get something like 2 zxyt plus 2 tyzx equal to 0. And so you take this term to the other side, and then you use this minus tyzx becomes ytzx. And so you get zxyt is the same as ytzx. And yeah, so that means if I interchange the first 2 with the last 2, then this inner product doesn't change. And so that gives me what I want. Okay. xyzt is ztxy. Okay. All right. Let me finish here. So Tuesday, we have a class, right? There's no holiday on Tuesday, as far as I know. Yes?
Yes, sir. We have a class on Tuesday.
Okay, fine, fine. So I'll see you Tuesday then. Okay, let me stop here. I'll